Uh, Very good evening to all. Uh, Now, in the morning session, I have just discussed how we perform the transposed convolution, that is known as the deconvolution. That's mean we are now able to understand the upsampling process. Now we know both the processes, convolution as well as that is the downsampling as well as upsampling process. So now we just go through a very beautiful architecture, and this architecture is being used for semantic segmentation. And due to this architecture, its name is given as UNet. So this UNet is developed by this OLEF, and basically this is developed for biomedical image segmentation, where we have histopathological or cytological images, and these images contain cells, different types of cells, and the purpose is to segment these cells or to extract these cells from the background. So definitely, it requires the segmentation process, and the major problem was which we face in biomedical image segmentation is it's the collection of the training data set. How we can get a trained data set. For that, we require expert pathologists, because without human efforts, it is very difficult to prepare prepare the ground truth images for the medical science. So that's why in this particular field in biomedical image segmentation, the number of ground truth images or training samples is very limited, and that's why if you apply the augmentation techniques also, still the number of ground truth images is very limited and can't be used to train a good CNN, which we have already studied. So to overcome this problem, this unit is basically designed, and it is uh, it is stated that this model can perform well in a very less amount of ground truth images as well. So this biomedical images where the annotation is very less, still this unit performs better for cell segmentation, and that's why this model is quite popular for the image segmentation of biomedical images, where we have to extract the cells. So, as we already have gone through that, if we use the LXNet, and it uses only 8 layers, and to train this model, 1 million training images are required to work it properly. But in such cases, in case of biomedical, we cannot collect this large amount of data, and a human being is not able to generate such amount of data, and that's why this is the limitation. And to overcome this limitation, this unit performs tremendously better as compared to other models. So this is the unit. Basically, it tries to learn the segmentation, where we have the input images, grayscale images, and these images contains the background as well as the cells are overlapping, cells are also there, but this beautifully it is able to segment all the cells. It can distinguish the overlapping cells as well, and that is the beauty of this unit architecture. So, and this is applicable, we can train this model with a very few annotated images as stated, and approximately 30 images per applications are only required to train this system. So that is the beauty of this unit architecture. So this is the architecture of a unit. Let's try to understand this architecture and how it performs the operation. So you will see here it's a U-type structure, and only few non-operations are being performed. You will see we are using some arrows over here. This the blue arrows. This blue arrow represent the convolution operation with 3 by 3 filter, and followed by a ReLU layer. So this is, you all know how we perform the convolution with ReLU layer. Then we are using these white arrows, gray arrows. In gray arrows, they are representing only cropping and copy and cropping function. Basically, we are performing some concatenation. I will explain this. So, and one more arrow which it is showing is this brown arrow. It is a max pooling operation by 2 by 2. So So you all know what is the max pooling operation. Then we have a green arrow. Green arrow, the up convolution means upsampling. And I have just in the morning session, I explained how upsampling process is being performed. And finally, this is the arrow, last arrow, which just represents the light green, which represents the convolution, one by one convolution. So we all know the all the operations. There is nothing new. Convolution is being used, and everything we have already studied. Only they have just attached all these layers in a beautiful U architecture, and that performs tremendously well. So let's try to understand how this model works. So here, if we give input image, so since it is a grayscale image, so number of channel in this image will be one only, and the size of this image is 572 by 572. So this is the input image. Now, first we will apply the sequentially we will apply two convolution. First convolution operation followed by ReLU, second convolution operation followed by ReLU. So input to this image is one channel input image, and now it is using 64 filters. It is using 64 filters. So here we are using a convolution, and with convolution width, you can see here this is the convolution operation. You all know here we are using a 3 by 3 convolution. 3 by 3 convolution we are using, and we are using an ReLU layer, and this ReLU layer, and this we are using 64 such filters. So you can generate the output. So output size will also be reduced because we are not using any padding over here. So now the stride size is 1, so the output size become 570 by 570. You all know how to calculate the output size by this n minus f plus 2p divided by s plus 1. This is the output. So if for this first convolution layer, the output size will be 572 minus 3 plus 2 into 0 divided by stride size plus 1. This is 570. So the output size of this image is 570 by 570, and then we apply second convolution layer with the followed by ReLU layer, and the size also again decreases to 568 by 568. So this is the first step. Of here also we are using the 64 number of filters. So you all know the operations. So this is not a tough process to understand now. Now next is the max pooling operation over here. Then the next phase we perform the max pooling to reduce the height and width. So here after applying the max pooling, the size becomes 284 by 284. Size becomes 284 by 284. So this is the size. Now after max pooling operation, definitely after max pooling, number of channels will remain 64. But after it, we have followed the convolution operation, two convolution operation with 3 by 3 filter, and now we have used the number of channels. Number of filters we are using 128. So now the output size after this two convolution operation becomes 280 by 280, and number of channels is 128. This is the second phase. Similarly, this step is repeated number of times. We apply after this we apply the max pooling operation. Then we apply the two consecutive convolution operation. Then we again apply the max pooling operation. Then two consecutive convolution operation. Then max pooling operation. Then two consecutive convolution operation. So these operations are being performed. So these are the this phase. In this phase you will see we are from where to we are reaching to what is available, where to what. Is it clear? So this is the where to what operation. Now what we have to do? Now we have to perform the upsampling process, because here only we can get the information that what is available over here. Now we are not applying any fully connected layer. We are ignoring the fully connected layer, and now we are only converting a upsampling process. Now we will deep back. We will just upsample the input value. For this upsampling process, this will be the input value, and you know how we perform the upsampling. The output of this upsampling will be larger in height and width, definitely. Now what will happen over here? Now you will see here, after performing the upsampling process, this is the output. Now actually here we only have a information, and that information is the what information actually. Now to get where it is available, So this information is get back from its corresponding layer of the downsampling process. So here its corresponding layer is this one, and its size is little bit different from the upsampling process, sorry, downsampling process. So what we will do, we will crop, we will just crop a particular part of this downsampling process, and we will then concatenate it with this, concatenate it with this value. So now the output of upsampling is only this one, but after cropping and comping this, concatenating this particular value, the size of this input becomes this one. Okay, so here we are performing two operations: concatenation. We are performing concatenation and copying and cropping and concatenation operations. And after this operation, we perform the two convolution again. We perform the two convolution with 512 filters. So this is the upsampling process. So here what we are doing, we are concatenating with high resolution features from contracting path. So this is the contracting path. Basically this is the contracting path. So here with the corresponding path, I am just taking a corresponding copy and concatenating it with the upsampling process, and then followed by the two convolution operation. This is the only thing which we are performing to get where the information is, and this step is now repeated. Now again we will perform the upsampling. It will give us the larger size image, larger size feature set, and then we perform the corresponding, we will perform the corresponding concatenation from its corresponding layer. Then we will perform two convolution again. Then we will perform the upsampling. After the upsampling, we will get some higher resolution output. Then we will concatenate it with the corresponding layer. Then we perform the two convolution. Then finally we perform the upsampling again. Then we perform the concatenation, and then we perform two convolution. This is the final output, two convolution operation. So here you will see here, after performing a number of times a convolution, upsampling, concatenation and convolution operations, now I have reached to this point. So here the size is 388 by 388. So somewhat almost you can say it is equivalent to the input size, larger size, high resolution image size, which can be used to visualize the output. But here the number of channels is 64. Number of channels is 64. But in segmentation, in image segmentation, we are talking about the cell segmentation. So if we have the cells, so this is a binary classification problem. You can say we have to provide two colors. One is for background, and second for cells. So that's mean only two types of pixel information are required. In semantic segmentation, I will classify each and every pixel into two classes. One is background, the second one is the cell. So finally what I will do, I will just perform a one by one convolution. I will perform here one by one convolution. If I apply the one by one convolution, only one filter, then only one output will be there. But I will use two filters because there are two classes in the output layer. So one by one filter with two filters I will use, one by one convolution, two filters of one by one convolution I will use. So it will generate two outputs, and these outputs will work as a semantic segmentation of the images. So you will see here how beautifully this network is used for the semantic segmentation. So this is the all about the UNet architecture. I think it is clear to all of you. Now, similarly, there are different types of applications are there in computer vision task. I have discussed only two. I have discussed the image classification, and then I have discussed the semantic segmentation. There are other categories are there, just like the image classification and localization. I have given you a hint in the image localization, where we can use one of the approaches. We can use you can say patch-wise classification, and that can be used for object localization. Similarly, we can use for object detection. So these are the different types of application that are being used by deep neural network, and we are getting the success in these different computer vision tasks. So in UNet architecture, this phase from where, because we are increasing what and we are reducing where, it is known as a contraction phase, and this is known as the expansion phase, because we are going from low resolution to high resolution images. So this is all about the theoretical part. in which I have just covered from the basics of the fundamental of the deep neural network. Then we have extended it for deep neural network, and then we have studied the different architecture of convolution neural network, how we can design the different architecture, how we can propose the different variations, and that can be applied to different computer vision tasks as well. So now let us discuss some few problems and which are the open challenges for the deep neural network. First one is the noise. Definitely this noise. If you introduce the noise in the images, then it is very difficult. It is very difficult to for the deep neural network to classify the images accurately. So the deep neural network is very sensitive to noise. So definitely for such cases, we have to pre-process the image, or we have to change some changes in our model so that we can handle the noise. So this is one of the challenge in the deep neural network. Second is the object categorization, how we are able to remove the obstacle. Our human brain is able to capture this cat behind this chair, but deep neural network is still facing how we can remove such type of obstacle, how we can tackle the obstacle. So how we can recognize the cat using these obstacles. So this is all about the deep neural network and its theoretical part. Now let's try to go through the implementation part, how we can implement this deep neural network. There are different libraries are available which you can use to design this deep learning architectures, different architectures, and you can use them for your own applications. So here I will try to give you a very brief and very simple part of the TensorFlow, so that you can initially you can understand how we can apply the TensorFlow, how we can design the deep neural network architecture using a TensorFlow, how we can implement it using a TensorFlow. So I will just cover very simple part. Once you are familiar with this simple, then you can go for more complex structures, more complex commands, more features, and which you can train, which you can input in your own network. So let's try to understand what the TensorFlow and how we are going to use this. So for this TensorFlow, we will use a cloud platform, and here to just demonstration also, I will use the Google Colab, and you all know the Google Colab is providing a cloud based platform, and basically it is very much like the Jupyter notebook, and you have already worked Python. I have just seen the timetable of your workshop, and there are number of lectures are there on this Python, so it will be helpful for you to understand the concepts of the TensorFlow that are very much similar to this Python. So here, this Google Colab provides a very good support, and here we can write the different description in form of text, images, also in the form of codes. Also, we can execute the codes. We can also select the different types of GPUs. We can select the performance devices, GPUs, TPUs, and there is no setup is required on your own machine. So definitely, and you can also share your code in GitHub. So lots of you can say in this open source environment, lots of facilities are provided to open up yourself. So you can open up yourself. You can participate in different challenges that are available online, and these challenges will give you some rank and will give you your own identity. So you can create your own identity. You can create your recognition on the online platform, and that will pay you in future. That will pay you in future. So and no and the companies are providing lots of research so that the people can come out, the good peoples which are not getting any other support, they can give their recognition through the online platforms. So here we are so that's why we are also using this Google Colab. So I think if you are not familiar, I just show you first the Google Colab, how we are going to work in this Google Colab. Let me share my first the complete screen, then I just again share the screen. So now my complete screen is visible to you. So now what I will do, I will just go through the Google Colab. So we can type Google Colab. So you can open this Google Colab. So here, if you have already a file, you can open that file. You can upload a new file, and you can take the file from this GitHub, and so all facility. You can also take the file from your Google Drive, and you can open the new notebook. So first, let's open the new notebook, and you will see here, this is just like a Jupyter, and you can write the code over here, just like you can write the code over here. You can just add more number of cells for the different codes. You can add the text. You can add your text to explain your code to all the online users, or if you want to send to someone, you can just put your information comments in this particular text field. You can also post your images as well. So everything can be run over here. Now you can select the hardware for. You can select the GPU, TPU, and you can select, and you can work out on your code in this particular Jupyter. Here you can just give your name, whatever you want to give it name. Last here we give it a GIT workshop, and we'll try to just demonstrate the different codes to this GIT workshop. You can also download it in your own OpenNote on system in Python code or in IPYNB if you want to work in this Jupyter Notebook in Colab online. So these are the different facilities are available, and which are very useful and user convenient. You can use these easily. Okay, so let's try to work on this Google Colab. Now here, let's try to introduce this TensorFlow. What is TensorFlow and how we are going to use it? So this TensorFlow is an open source library, and nowadays you are seeing that everything is generally is an open source, and that's the beauty. Then you can also contribute in these open sources, and you can also propose your own libraries as well. So here, this is an open source library, and which is developed by this Google Brain team. And basically this TensorFlow is designed for the machine learning, to design the machine learning, different machine learning architectures, and the deep neural network architecture. So here, we here in this TensorFlow, we are able, this TensorFlow is comes up with different types of functions, and you can easily work out. There are different versions are also available. Now we are working in TensorFlow 2 point something versions, and in TensorFlow 1 point version, there are lots of complexities was there, and lots of ambiguities was there, which are being removed now in TensorFlow 2.0. And this TensorFlow 2.0 is very much similar to Python, and we can easily work out. You can see very simple commands are there, very simple functions are there, and we can easily, there is no ambiguity, no, you can say a user can easily understand the concept, a programmer can easily understand the concept. So now why TensorFlow? You all know it's a Python library. Definitely, it's better, and if we can deploy our system on any one of the CPUs, GPUs, TPUs, and any server, any mobile devices, we can deploy anywhere if we want. So interportability is available over here. There is lots of functions. Auto differentiation is there. There is no need for find out the derivative, and that's why we easily find out the back propagated the derivations in our deep neural network. That is the most complex part. And definitely in internet awesome projects are available using TensorFlow that you can go through, and lots of competitions are open where you can take participation, and you can also earn the money by winning the competitions. And different companies, big companies, are also using this TensorFlow, like Google, OpenAI, DeepMind, and so on. So now why TensorFlow? Basically, there are lots of deep learning libraries are available. Talk is there, Theano is there, Cafe is there, and but still the popularity of the TensorFlow is better as compared to others, and that's why we are going through this TensorFlow libraries. So let's start with the TensorFlow examples, very simple example, and try to understand how we can perform this TensorFlow examples. So now so in this example, what we are going to do here, to understand the basic steps or basic commands in the TensorFlow, we are going to run this expression to implement this expression. This expression is a equals to b plus c into c plus 2. So here we are going to implement a TensorFlow program to execute this statement, to get the output of this statement. So how we can perform this operation? So the basic the first step is we should have to break these statements. So why we have to break these statements? So you can see here we are breaking this b plus c and a separate statement d equals to b plus c. Then we have just calculated the c plus 2 and stored it in e equals to c plus 2. Then we perform the multiplication of d into e. This way I am calculating this a. Now why I have broken these? Why I have broken these? So the reason behind it, once I just broke this expression into multiple expressions, then I can perform these operation parallelly, because this expression and this expression are independent. Once these statements are independent, that means I can perform this statement on one machine, I can perform this statement on second machine. So you are able to perform these operations on two different machines, and that will enhance your computational power, or you can say you will gain in computational times. And that is the beauty. Okay, now you have to design the problem as well, okay, how we can perform the different operation on different machines parallelly. So you have to find out those which are independent, and then you can gain in terms of computational time. And if the application is very based on the big data or deep learning network, so this parallelism is very important to know. So this is the TensorFlow. That's why we are trying to broken this particular expression into number of statements. Now what happens, basically this TensorFlow works on the data flow concept. In data flow concept, what it did, actually we try to make the flow graphs, data flow graphs. Here in data flow graphs, each node represents a operation. Each node represents an operation. So for example, this is B representing, this is C this is represent the particular operation addition. This is a second addition operation. Finally, we are getting this multiplication operation. And these arrow represent the flow of the data, and this data in TensorFlow is known as tensors. Flow of data is in terms of tensors. So data is known as tensors, not data. So actually what we are doing, we are only transferring the data from one node to another node in terms of tensor. So we generally work in this data flow diagram. Now you will see what the tensors are. So all the data, we representing the data in terms of tensor, we call them as a tensor. That's why it is a TensorFlow analysis. So here you will see here that scalar, if the number or there is a scalar number, then we call it as a zero dimension tensor, zero T tensor. Okay. And if we are using a row vector or column vector, then it is known as one dimension tensor. So we are just given a new nomenclature of the numeric values or other values. If I have a matrix, two-dimension matrix, then it is a two-dimension tensor. So that's why we are talking about the tensors in place of the data. Now let's try to make the first network data TensorFlow example for this problem. So let me show you. So let's try to make this code, and you will be able to understand how we can perform the operation using TensorFlow over here. So now the problem is, we just type the problem, what we have to do. Let me just put this back. Okay. Now what I have to do, I have to solve the expression a equals to b plus c and into, then I have to perform c plus d. I have to perform this operation, and secondly I have to find out the output. I have to find out the value of a, and for that I have just broken this particular expression into three expressions. So d equals to b plus c. First I will solve d equals to b plus c, then I will solve e equals to c plus b, then I will solve a equals to d into e. So this way I have to solve these expressions. Okay. So I have to make the code for this particular expression. Let's give some gap so that no confusion should be there. Okay, so now the first step in this expression, in this making a program for any particular problem, is we have to declare the variables and constants. So we have to declare the variables and constants. So we can write, just like we can write the messages, variable and constant declaration. So it will help the you can also make them sorry, you can also increase the size. You can also change the different structure which you want to show to your users. Okay, so it will be more appealing. So now we have to declare the variables and constants in TensorFlow. And before declaring this, first I have to import the TensorFlow library. So I have not imported, so let's import the TensorFlow library just like we do in Python. Import TensorFlow as, we can give it a name, TF. Okay, so this is the, we can run it from this place. So we have, now this way we can import the TensorFlow. Now we have imported the TensorFlow library. Then we can declare the variables. So how to declare the variables and constant? So first I have not taken any constant over here. I just take a constant. We just take here a 2. We just take here 2. So this will be b plus c. This will be c plus 2. C plus 2, and then d into e. Okay. Now first we declare a constant. So we can write constant is equals to tf dot constant. Now you can see here different options will appear. So we can type constant. Yes, constant is over here. I will press the enter. So I will get the tf dot constant, and then I can assign it a value 2.0. You can see here the description is there. You can also take the help of Google if you want to understand more detail about the different objects. So I can write 2.0. So this is the constant which we have declared. And here if once a value is assigned, the automatically its type and its value will be assigned to the constant. Now next we have to declare a variable b, because we have to solve this b plus c. So I have to declare two variables b and c. Okay, so now first I will declare a variable b equals to tf dot variable. So there is a capital V. It's a case sensitive, so we have to write capital V. So variable is now available. I just press enter. Tf dot variable. Now I can initialize this value. I just initialize this value to 2.0. So there are more number of parameters you will see here. We can set it. It is whether it is a trainable or not, and parameter. We can also select its type. Specifically, we can give it its type. Here, if we are not giving the type, it will automatically take according to the value which we are assigning. So different types of other features, properties are available which you can use. There now here we are only using very simple explanation. That's why I'm just using a very simple features. So now I have declared this variable b. Now I can use this variable c. So I can declare c equals to tf dot variable, this variable, and then I can assign it a value. Let's take 3.0. So this way I have declared all the variables. I have declared b, I have declared c, and I have declared 2. So all these variables, because they contains b, c, and a constant, all these three are declared. Now I can execute these statements. So there is no error. So now we move forward further. Now we have to perform the operation. So we can write here the TensorFlow operation. We have to write TensorFlow operations. Okay, and we can write this TensorFlow operations. Then we can go for code. Now this is the TensorFlow operation. Now what we have to perform? first we have to perform the addition between B and C. Addition between B and C. This B and C are the variables. So it is very simple. There are very simple functions are there. We can write D equals to, we have to write D equals to B plus C. So we can write TF dot, which function? Add. There is an add function. This is a add. So we can write add. Then there's the values which we have to assign. The first value we have to give B, then comma C. So this is the D equals to TF at B comma C. So we have performed this operation. Then we have to perform this addition, constant and C value. So E, we have to store it in E. We can write E equals to TF dot add, let's add, and then we can write C comma the constant which we have assigned, we have already declared. Okay, this is the constant which we have declared. Okay, so this is the E value. And then finally, after performing these two operations B and D, I have to perform the operation A equals to D into E. So I will write A equals to TF dot multiply. These are simple nominations are there, so you can use these nominations. And I have to write D comma E, D comma E. I have to write A equals to So these are the three operations which I have to perform. Now after these operation, now I have to execute, I have to just print the value of A. I have to print the value of A. So now initially in TensorFlow 1, we have to create the sessions, and using the sessions we can only able to run these statements. But here in TensorFlow 2.0, now the sessions are replaced by the eager execution. Eager execution. So these eager execution are very much similar to the Python, and there is no need for any. There is no ambiguity in the statements. There is no session is required now, and we can directly print the value just like in Python we use. So now we have to print the value of A. I will write print the variable value of A is. I can use, you already perform the Python workshop, so you have the knowledge. And if someone has worked in the TensorFlow 1, so definitely it is different in this scenario. TensorFlow 2.0 is much easier than TensorFlow 1. So now I can use format. There are other ways to print also, so I can write over here A. So when I will just run this statement, now you will see here I get the value of A is 25. So this way it's very simple. You have seen how beautifully we are able to execute. We are able to make the program in TensorFlow. It's very simple to make the program in TensorFlow. Okay. So now, so we have seen here how we have made the program in TensorFlow. We have imported the library first, then we have created the constants, we have created the variables, TensorFlow variables, then we have performed the operation, and just like for Python, this is known as eager execution, and we can print the value of the output which we want to print. So this is the TensorFlow examples. Now, similarly, there are different types of constants you can design. You can just declare, just like in Python, we can declare this. Initially we have declared a constant, that is a scalar 0D tensor. We can declare 1D tensor. 1D tensor means one dimensional array, just like this tf dot constant. If I write 2 comma 2, so definitely it will create a tensor with value 2. And here you will see, here we are giving a name. Basically, if you want to give a name, so this name can be used in the data flow. So if you can skip this part also. Now we have, if we want to create a 2D tensor of constant values, we can write tf dot constant 0 1 comma 0 2. You all know how we can create the 2D tensors also. So this is the way we can create the tensors. Furthermore, if you want to create a tensor of a particular size, but whose all values should be initialized to 0, so we can use 0, just like in zeros we use in Python. So we can use tf dot zeros, and 2 comma 3 is giving us the size. So automatically 2 by 3 matrix is generated. 2 by 3 matrix will be generated, and here I am using the type. Type means we can use a different type. I will show you the different types available. So tf.int 32 means all the values are of integer 32 bits. So here a 2 by 3 matrix is generated, all values are assigned to 0. Similarly, we have tf.fill, and this tf.fill will create this matrix of 2 by 3 size tensor, 2D tensor, and will fill all the values to 8. In place of 0, it will fill all the values to 8. So this is way we can create more number of different types of tensors. Now, similarly, we can create more constants just like sequences you have used in Python. We can use linear space. Tf.tf is a TensorFlow object which we have created. So linear space contains that three values: start, stop, and num. That's mean it will start from 10, it will go up to 13, and how many values it has to generate? 4. So automatically it will create the gaps and it will generate the 4 values between 10 to 30. So this is a linear spacing, linearly generated numbers. You can generate any numbers in between up to particular ranges. Similarly, range, which you have used in Python in for loop, for I in range, you have used. So similarly, here we also use a range. So here tf.range we can use. Range can have 3 values as well as only single value. If I can use start, comma limit, comma delta, and if start is 3, so it will start from 3. Limit is 18. That means it will go till 18, but 18 is not included. Okay, and delta is the difference, how many differences you have to create. So we have taken here the value of delta is as 3. Value of delta as 3. So that's mean it will start from 3, then next number will be the 3 difference 6, then 9, 12, and 15. It will not return the 18 value. As you know, in range, if I use range in Python, what happens if I write only tf range limit? What do you mean? The meaning of this? Its meaning is it will generate first value 0. It will start from 0 and it will go till 4. It will go till 4. One value less than the 5. So that is the constants which you can use in your programming. In your program, if we are using in for loop, you can use the range function also. And there are different data types in TensorFlow which you can use. We'll use in our future exercises. We can use float 32, float 64. You all know the 32 and 64 bits data is the number of bits that is required by these. We can use int 18, int 16-bit integer, 32-bit integer, 64-bit integer. We can use unsigned integer, 8-bit unsigned integer, 16-bit. We can use int string. We can use boolean value, and all the we can use the complex numbers, and different types of data types are available. You can go through the data types. Okay, so I think I should stop now. Next, in the morning class, we will implement the first linear regression using the gradient descent using this TensorFlow. Okay, and for better understanding, you can go to the tensorflow.org's website to understand the concept. So now the session is open for the queries. You can ask the queries, please. Yes.
Participants have any queries, please ask.
Okay, sir. I think there is no query from the participants, and so we should bind the 2 days class, and we'll continue in the morning class.
Okay, sir. Thank you so
Okay.
much.
Okay. Thank you very much.